The recent spotlight on 3I/Atlas, our third confirmed interstellar visitor, has grown brighter with every new observation, and for good reason. This object, arriving from somewhere far beyond the gravitational influence of our Sun, brings with it a treasure trove of scientific data that continues to challenge long-held assumptions about comets, their structure, and their origins. Since its discovery, astronomers around the world have been eagerly directing telescopes, both ground-based and orbital, toward this unusual and scientifically precious visitor. Every new dataset seems to reveal additional mysteries, and a newly released pre-publication study from researchers at the Auburn University Department of Physics has added another fascinating layer to the story, this time focusing on the comet's water content and how it behaves as it approaches our Sun. Comets, as we know them from our own solar system, almost always contain water in the form of ice. Water is one of the most abundant molecules in the universe, forming readily in cold molecular clouds where comets and planets originate. Despite this abundance, liquid water is rare across the planets and moons of our solar system due to temperature, atmospheric, and geological constraints. But in icy bodies like comets, water is typically preserved deep below the surface. As these comets travel inward toward the Sun, the rising temperature causes the ice to sublimate. Sublimation is the process by which a solid transitions directly into a gas without becoming a liquid first. And this gas forms the glowing coma and long, sweeping tail that make comets some of the most visually stunning celestial objects visible from Earth. Astronomers often track specific molecules produced during this sublimation process because they reveal clues about the comet's composition, history, and the physical processes occurring on and below its surface. However, 3I/Atlas does not behave like the comets we are familiar with. The comet was discovered when it was about 6 astronomical units, AU, away from the Sun, well beyond the orbit of Jupiter, and it has been steadily moving closer on its one-time path through the inner solar system. Observations suggest that it will reach its closest approach to the Sun, known as perihelion, at approximately 1.3 Australian dollars in October. What makes the Auburn team's findings remarkable is that they were able to detect water-related activity at a distance, where such activity is usually extremely weak or entirely absent. Using the ultraviolet/optical telescope UVOT aboard the Neil Gorell Swift Observatory, which orbits Earth and therefore avoids atmospheric interference, they observed 3I/Atlas in late July, roughly a month after its discovery, when the comet was still 3.5 Australian dollars from the Sun. At this distance, sunlight is generally too weak to sublimate water ice efficiently, meaning astronomers do not typically expect strong water signals from comets this far away. Yet the team detected something highly unusual, a strong emission of hydroxyl OH molecules, which serve as a reliable indicator of sublimating water ice. OH is produced when ultraviolet light from the Sun breaks apart water molecules. Detecting these emissions so clearly from an object at 3.5 Australian dollars suggests that 3I/Atlas contains either an unusually large amount of water or is structured in such a way that water sublimation occurs more readily than in typical comets. Adding to the mystery, the researchers did not detect any sign of cyanogen, CN, a molecule commonly found in comets, and one of the earliest volatiles to sublimate due to its relatively low sublimation temperature, about -13 degrees Celsius. CN has a prominent emission band that easily passes through Earth's atmosphere, making it one of the first signatures astronomers look for. Its absence in these observations strongly implies that the composition of 3I/Atlas is markedly different from the standard chemical profile seen in most solar system comets. Another significant outcome of the observations was the calculation of the comet's active surface area. This measurement provides insight into how much of the comet's surface is actively producing water vapor. According to the Auburn study, approximately 19 square kilometers of the comet's surface appear to be releasing water. Given that the estimated maximum diameter of the comet is 2.8 kilometers, the total surface area would be a little over 24 square kilometers. That means roughly 20% of the comet's surface is active. far more than the 3 to 5% typically observed in comets from our own solar system. Such a large active fraction suggests that 3I/Atlas is exceptionally pristine. If this is its first ever close encounter with a star, as is strongly suspected, then its ices have likely remained untouched for billions of years, unaltered by repeated warmings that solar system comets undergo. This pristine nature could explain why it contains so much water near the surface, and why sublimation begins even at relatively great distances from the Sun. This unusually high water production sets the stage for a critical test as the comet approaches perihelion. The Auburn researchers proposed two possible scenarios based on the comet's future behavior, each of which would reveal important clues about its origin system. In the first scenario, if the water production rate increases significantly as 3I/Atlas nears the Sun and continues to dominate the emission profile, with only trace amounts of other volatile compounds such as carbon monoxide or cyanogen, it would indicate that the comet originated in a low metallicity environment. A low metallicity system is one in which hydrogen and helium dominate, while heavier elements and the molecules formed from them are relatively scarce. Such systems are believed to be older or formed in regions where fewer stellar generations have enriched the local interstellar medium with heavier elements. In the second scenario, if the water sublimation rate peaks before or near perihelion and then rapidly decreases while emissions from high metallicity volatiles increase dramatically, this would suggest that 3I/Atlas was formed in a high metallicity system. This outcome would make it chemically more similar to 2I/Borisov, the second interstellar object identified in our solar system, which displayed high levels of carbon-bearing volatiles that indicated its origin in a relatively metal-rich environment. The contrasting chemical signatures between 3I/Atlas and 2I/Borisov would show that interstellar comets can vary widely in composition based on the conditions in their home systems, much like comets in our own solar system do. The coming months are expected to be filled with intense observational campaigns as astronomers worldwide attempt to monitor every stage of 3I/Atlas's journey around the Sun. Its relative brightness, unusual chemistry, and the scientific importance of interstellar objects make it a prime target for telescopes ranging from small observatories to some of the most powerful instruments available. Each new dataset will help refine our understanding of how different the comet is from solar system comets, how interstellar environments influence the formation of icy bodies, and how this object has evolved across potentially millions or even billions of years of interstellar travel. As it approaches perihelion and its activity increases, more gases will be released, revealing deeper layers of its structure and composition, layers that have remained unchanged since the early days of its formation. Objects like 3I/Atlas are rare opportunities for scientists to study material that formed around another star and has traveled across the vast emptiness between stellar systems. These cosmic messengers bring with them chemical signatures and physical characteristics imprinted by the processes and environments of their distant birthplaces. With each observation, astronomers move closer to answering fundamental questions about the diversity of planetary and cometary systems throughout the galaxy. As 3I/Atlas melts further and reveals more of its secrets, the world will be watching closely, fully aware that such moments, glimpses of objects born around other suns, are among the rarest and most valuable events in modern astronomy.